So let me first start introducing the terminology on which we will be talking. So the first piece of terminology is talking about states. So states, we will call them consistently S when we're talking about an individual state, and they all come with some set of states, capital S. And for the sake of our conversation today, we will assume that all the states observed. So in this case, again, I have 8 states, and the robot, or in this case I would call myself I know exactly where I am standing. So it's called observed case. Doesn't have to be necessarily this way, but we will assume that everything is observed. Okay? So I would say observed. The next part of our description would be action. What you actually can do in this space. So we will have actions, and I will call them consistently lowercase a. Okay? And what are those actions? Those actions are things that you are allowed to do. So in this case, we would assume that the agent can go left, right, up, and down. Okay? Those are the 4 actions that you can do. And let's say if you're taking an action and you're hitting the wall, you're staying maybe in the same place where you are. So this is a very small world. If I just defined you that and just explained to you thinking, what is a big problem? You know, let's say I'm here, I just need to go around and I'm getting 2 + 1. What's so special about this problem? It's just a planning problem, you know, that is my starting state, that is my destination state where I'm getting the highest reward. Why do we need to introduce some new machinery? Planning will do it for us. However, what's interesting about it, that we are operating in non-deterministic world. Non-deterministic world means that maybe I want to go straight, and I would eventually end up going straight, maybe in 80% of the times, but there is 10% chance that I may go right or I may go left. And that's what makes this problem particularly interesting, because even though you may have good intention and you know where you want to be in, but you may end up being in a different place. It's exactly like in life, correct? We have good intention, but may end up somewhere else. So that's why we will introduce a new notion, which is called transitions. So transition will take state from which you start, then the action A that you are taking, and the destination state, okay? And it will give you probability of ending up at state S prime when you have taken action A from the state S. This is a transition. So for our case, we would assume that we have 80% probability to follow the direction which we intended to take, and then there will be a 10% chance that we will go to the sides. So you can imagine yourself creating a very big table that say that if you are, let's say, in this state and you take this action up, 80% you're going to end up here, 10% you're going to end up here, and 10% you're going to stay in the same place because there is nowhere to go. Okay, so this is our transition function. And the final thing that I want to introduce you is a notion of reward. Okay, because we said that this is our way to see what is a good behavior, if at the end we got a reward. And there are many ways to define reward. So what I kind of implied here, I told you that if I'm taking, you know, the only reward or punishment that I'm getting are in these 2 states, so I can define reward as a function of state. Okay? In other problem, this definition is not sufficient. Like, for instance, in the examples that I gave you from the marketing case, you actually not only care where you end up, you also care, you know, how much it costs you to do something. So maybe in this case, you may want to define reward as the function of the original state, the action, and the state where you end up going. So whatever I'm going to be describing today will work both with this reward or with this reward. Both of them will be totally acceptable. And when we're talking about Markov decision process, we're actually thinking about, we would assume that both the states, action, transition, and rewards are given to us. So pretty much we can say that MDP, Markov decision process, is just a quadruple of all these values. So it will be S, A, T, and R. And you can add some extras to it. For instance, you can assume that there is some starting state where you have to start. Doesn't have to be so, but you can decide that there is some starting state. You can also assume that there are some states which are kind of halting states, that once you arrive there, you cannot continue anymore. Once, let's say, you arrive here, you got your +1 reward, you are done. So there are all the extra variants of these problems that you can consider, but everything that we are discussing will be applicable to all these different variants of the problem. So for now, let's just look again at what is MDP. So in this case, we have a set of states, we had a set of actions, and you can think about this transition just as a very big table that gives you a probability for every triple of state, action, and another destination state. And finally, you have a reward, which can again be written just as a table of values. Now, when we will start thinking about more realistic problem, when we want to have a more complicated definition of transition function and the rewards, but for now, for what we're discussing today, you can just imagine it as tables.